What does a meme, a banker, and COVID have in common? Well, the relationship can be explained by this Venn diagram, but the one thing to unite them all is the idea of compound growth. The growing popularity of a meme, the spread of COVID, and the compound interest the bank charges you. In this video, I will show you how to use the rule of 40M to estimate the return of anything that have a compound growth. Let me begin by showing you some symbols and formula. For anything with a compound growth, the future value FV is equals to the present value PV times 1 plus the growth rate in percentage raised to the number of periods, N. And the rule of 40M informs us that the R can be estimated by doing a simple division of 40M and N, where M is just how much our total value increased by. If our future value is twice our present value, then M will be equals to 2. Although the rule of 40M works for anything with a compound growth, let's just use an example of estimating investment return. M is chosen to be the increase in value because M represents multiple. It can be the multiple of money, MOM, or the multiple on invested capital, MOIC, depending on the situation. When M is equals to 2, your investment have doubled in value. And when M is equal to 3, the investment tripled in value, etc. R represent rate. It can be the interest rate, investment return, growth, compound annual growth rate, CAGR, and internal rate of return, IRR. N is just the number of periods. It represents the holding period of the investment in this case. Let's just use an example of buying and selling a house. Let's say you buy a house today for $100 and sell it 4 years later for $300. In this case, the multiple would be 3, since the value of the house essentially tripled in value, and the number of years would be 4. Using the rule of 40M as an estimation, the return would be 40 times 3 divided by 4, which would be roughly 30%, pretty close to the actual return of 31.6%. If you have an option to sell the house a year after for $400, should you do it? Using the rule of 40M, having the multiple of 4 and number of years as 5, you will be able to estimate the return is roughly at 32%, virtually the same as the actual return of 32.0%. But of course, in this case, you will need to think about if the marginal increase in return justify the risk of selling the house a year after. And if you want to be more conservative and selling the house for $200 at year 3, using the rule of 40M, you'll be able to estimate the return at about 27%, pretty close to the actual return of 26%. Some people may say, hey, I know this trick from somewhere else. Isn't this just the rule of 72? Or the rule of 70? Or the rule of 69.3? Well, those rules are only for when M is equals to 2. As I've shown before, the rule of 40M works for the multiple of 2, 3, and 4. And it also works even if the multiple and the number of years is not a whole number. In this case, where you sell your house at $250 after 3.5 years, the return would be estimated at around 29%, pretty close to the actual return of 29.9%. Now that you understand how it works, let's dig deeper and understand the why. Why does it work? To understand why, we have to take a step back and look at the original equation to calculate future value. By rearranging the term and dividing both sides by PV, The left-hand side is just m in this case. Taking the lateral log to both sides and moving n from the index to the multiplication, dividing n to both sides, and switching the size of the equation, you will be able to observe that log 1 plus r divided by 100 is just some constant divided by n, which is the input of our rule for the n. To further evaluate the left-hand side, we have to use something called the Taylor series, aka the second most famous Taylor S in the world right now. So Taylor series is just a polynomial representation of analytic functions. Here are just some examples of how you can represent different functions in terms of infinitely many polynomial terms. Well, most of this representation is not helpful. The first one looks awfully similar to our previous equation. Expanding the left-hand side of the equation using the Taylor series, you are able to get this new equation. And if we look at the second term of the left-hand side, r is sufficiently smaller than 100 in our investment case, so that r divided by 100 raised to the power of 2 is quite small. And using the same logic, you can see that the next term is even smaller, and the term afterward is exceedingly small. It's fair to say that all of the terms after the first term is just an error term. Adding error to both sides of the equation and multiply both sides by 100. Since we know that 100 times a constant is still a constant and 100 times error is still an error, we will able to see that r is equals to a constant divided by n plus an error term. Since the error is quite small, we're able to say that r is roughly equals to some constant divided by n, or r behaves like constant divided by n. And it is indeed the case. Taking m equals to 2.5 as an example, the pink curve shows that the estimated r behaves similar to the white curve, the actual r. The actual r here is just calculated by rearranging the term from the original equation to calculate the future value, which I will not go into details. Now we understand why r behaves like a constant divided by n. The final piece of the puzzle is why 40m is chosen to be that constant. I would say this part is actually relatively uninteresting. It's actually found by a process of trial and error. Let's say that we have chosen 72 as the value of k. We're essentially saying that we're estimating r using the rule of 72. And I've limited to the following scenario, where m is equals to 2 to 5. And the best k is chosen when it minimizes the total error for when n is equals to 3 to 7. Let me show you what that means. For example, when m is equals to 2, I've chosen 72 be our value of k. In the table below, you can see the actual r and the estimated r for different value of n. For example, the first value of the third column, 24, is just calculated by dividing 72 by 3. You can then calculate the error for each value of n, and adding them up, you can see the total error comes up to be 3.8. And using the same process for different value of k, I'm able to find that the best value for k when m is equals to 2 is actually 75. 75 is the value of k that minimizes the total error. So I've put 75 as our choice of k for when m is equals to 2. And the best value of k for when m is equals to 3, 4, and 5 is 126, 165, and 198 respectively. And in the table, you can observe that 75 is roughly equals to 80, 126 is roughly equals to 120, and 198 is roughly equals to 200, which coincidentally just equals to 40 times their corresponding value of m. Putting all this value in a xy coordinate, you are able to observe that 40m is indeed very similar to the best value of k for when m is equals to 2 to 5. You may ask if the rule of 40m extend beyond m is equals to 5. The short answer is no, and the long answer is absolutely not. If you extend the coordinate, finding the best value of k for up until m is equals to 25, you'll be able to see that the relationship is not exactly linear. Even if you fit another linear line for any value beyond m equals to 5, I would say it's still too complicated. You might as well just memorize some special number in the table on the left-hand side. Since we're living in a world of compound growth, the rule of 40m has a wide range of applications, from banking and finance, population growth, disease modeling, to subscriber increase analysis. You would also know how to move from the original formula to calculate future value to the relationship between R and log m over n, and in turn understand the rule of 40m. And if you're familiar with the concept of continuous compound interest, you're able to notice that the left-hand side of the second equation is just exactly that. Using small letter r to represent the continuous compounding growth and t to denote the continuous time, r is just equals to log m divided by t. And rearranging the term, you'll be able to get e to the power of rt is equals to m, which would give us that the future value for any continuous compounding growth is just PV multiplied by e to the power of rt. So for anyone that is studying math, engineering, or financial mathematics, I'm sure that this would not be the first time, and definitely would not be the last time you will see something like e to the power of rt. And for continuous compounding interest, we would not be needing a rule for estimation, because r in this case is just equal to exactly log m over t. And this is also one of the reasons why continuous compound interest is used in a lot of cases. It makes the calculation easier, and especially make taking derivatives much easier. So to consolidate your knowledge of the rule of 40m, here are some practice questions that you can do. And here are some more questions. For these questions, you can be able to observe that the rule of 40m also have its limitations.